Right. So, hello everyone, and welcome to today's talk. We are glad that you guys were able to show up after this talk got postponed from Friday to today. And yeah, so today's speaker is Sumeet Kulkarni. He is an alumnus from 2017 batch of BSMS from IIT Pune, and right now he's doing his PhD from the University of Mississippi in the US. His work involves various aspects of gravitational waves. But today he is not going to talk about his work. He's going to talk about his favorite hobby. And yeah, let's just enjoy a chill talk today and learn something new. I guess that's it. Sumeet, over to you.
Thank you so much. Thank you for all the team at Aakashganga to have me here again. I'm happy to be responsible for extending your Astro Week for a few more days, thanks to a series of unfortunate events on Friday. But for those who have rejoined, I thank you for your patience on that day. Thank you for your time, and I'll make sure to make it worth it. So I'm here to talk about astrophotography, which it still feels too soon to describe as a hobby, because if you had told me this time last year that I would be giving a talk on this subject, I would have laughed, because it really started like after the pandemic. I wanted reasons to get out, and I happened to have the gear that could help me start, and I hope that you will be able to pick it up as well. It's been really rewarding. It's something that I don't mind staying up late, whether it's cold, waking up early in the morning, and at the end when you shoot some images, process them, it's going to be really helpful. So I'll start putting up my presentation. So you should be able to see the presentation on the screen, so which is basically the world's worst title slide. And that's what you come to expect when you take a raw image of some like deep sky object, something that's going to be really dim, like a nebula or a galaxy. These pictures that you see, the beautiful pictures, you might see them on Astronomy Photo of the Day, APOD, the NASA website, or really anything, the super crisp, clear, beautiful processed images, they're a long way from what you actually get out of the telescope in the first instance. So you see all this, this photo looks dirty with little white specks. They are not stars, they are noise, it's thermal noise. You see some dust specks on it, that's actual physical dust on the filter. And behind you might see a little hint of what your subject will be. So I'll tell you why we have this kind of image to begin with, and what we can do to make it better, to process it in order to get something that's clear. And that's what you want. So I labeled the talk as "The Sky is Your Canvas." So that's something that just came right out of my head. But when I thought about it, like, the sky is not really your canvas. The paintings are already there. The pictures are up in the sky. And as an astrophotographer, what your job is to basically clean the canvas and then display it for everyone else to see. So I've structured my talk in kind of a non-linear fashion. So I'll be starting with telling you what elements are necessary to make good astrophotos, but I'll be talking about it in terms of using like the state-of-the-art gear. Like, you have a telescope, you have a good CCD camera attached. And I do this because when you have the entire gear, that's when you need all of these elements, and you need to be very careful about them. But then I will talk about how I started out, which was with something very little. And at that point, you need to still keep the basic elements in mind, but you can also work with like minimal gear and still really get some great pictures. So these days, I am blown away with the ability of smartphones also to take pictures, but I don't really know a lot about them. I don't own one of these new expensive smartphones, but I'll be focusing on what you can do with something like a manual camera, like a DSLR or a mirrorless camera that you can use or borrow and click some good pictures. And if you're here for just looking at pretty pictures, that's going to be the second part of my talk. So to just give a little bit of historical basis, because all talks start with some history, but I really don't know much background about astrophotography in general. But just 100 years back, this was 1923, when astrophotography was more science. Like people were going beyond observing things with their naked eyes and then putting things down onto photographic plates, which had some photosensitive material on a glass plate that was exposed overnight. And if there's any football fans in the audience, looking at that VAR will give you slight goosebumps. But what this photo with VAR taken by Edwin Hubble shows is it's an exposure of the Andromeda Galaxy. It looks nothing like a galaxy, right? Because well, it's an old photo, and that's what people thought at that time, that the Andromeda Galaxy was just another huge nebula in the sky. But he made this observation that some of the stars at its edge were variables, and these are known as Cepheid variable stars. So if you study how much they vary, like what the period of their variability is, you can figure out how far they are away from us. And it's crazy to think at as little as 100 years ago, we knew about the general theory of relativity, but we thought that the entire universe was basically our own galaxy, the Milky Way. And then when he used these variable stars to measure the distance to this gas cloud, the Andromeda gas cloud, he calculated that it was actually outside the Milky Way. He found something that was outside the universe. And this is just something I find really interesting. I saw this plate in the Smithsonian Museum in DC. But we've come a long way since being able to, like these being the scientific images of cutting edge research, to the kind of images we can take with our phones that are so much more clear, offer so much more clarity. So I'll talk about like as I said, the basic elements to get good astrophotos. And the first one is the first couple of them are shared with any kind of photography, is that you have to be at the right place and at the right time. Oops. For images, like if you're trying to get a landscape of the moon, it's obvious, like you have to think a lot about how you're going to frame the shot. And this is a beautiful one taken in Dubai. For imaging stuff like the Milky Way, or if you want to hunt for some deep sky objects, you have to kind of prepare early by using tools like Stellarium, or you can use an app to make sure that your object is going to be high up in the sky towards the zenith, so that it's away from the horizon where there's a lot of atmospheric scintillation and the seeing is really bad. So make sure that all the objects are up, and this would really help improving the quality of the shot. You have to be obsessive of getting the focus right. So as I said, all astrophotography, you have to work with manual focus. I haven't heard of any autofocus system that can focus at stars, because the focus needs to be set at infinity. The stars are at an infinite distance away from us. In practical terms, to do the focusing, you have to like pick a bright star, or it could be a planet, and make your focusing adjustments such that it looks like a pinpoint. And some systems have like a live view magnification, where you can magnify the view maybe 10 times, and that really helps you getting that thing sharp. The third thing, everything in astrophotography or your targets, unless you're imaging the sun and the moon, everything is really dim. So you have to be hungry for photons. You have to make sure you get as much data, as much light in your images as possible. And that includes two things. You can take your image for a longer time, keep your shutter open for a long time, or you can use a wide aperture, which is basically the size of the opening of your camera shutter, how wide it can open to allow light in. Some lenses have apertures that you can control. If you're using a telescope to do the imaging, that's something that's fixed. That's the size of your lens. That's something you have paid for. If that's the case, you can increase the light by taking longer pictures. But of course, you can't get too greedy, because if you try to take too long exposures, you run into problems. The most significant of them being noise. So that's like the fourth thing, that noise is inevitable. You can't avoid noise, but you have to be creative. You have to try out all means to remove it as much as possible. So as I said, these four elements, I'm going to start talking about them by looking at the good equipment, which on the camera side of things, like you can attach this to the best telescope you have. And as far as the telescope is concerned, you get what you pay for. But again, on the camera side, we usually work with CCDs, charge coupled devices. And that's also true for astronomical images that are taken for scientific surveys and studies and so on. So this is basically an array of light sensitive pixels. And as photons into them, they build charge. And after, if you take an image for a certain amount of time, that charge buildup is read out as a pixel count. So more light falling onto a pixel gives you a higher pixel count. And at the end of the photo, all of it is read out together. Now, the advantage of CCDs over any other kind of conventional cameras like webcams or DSLRs is that they have much greater image depth. And by depth, it means each pixel can support count. It has a memory to store data for 16 bits. And that means it can store 2 to the power of 16 numbers. That happens to be this number, 65,536. And each number can represent a shade of gray. And gray, because actually, if you want to do sensitive imaging, you have to do it in black and white, not in color. And the reason is simple. If you do it in black and white, you can do it, you can store the 65,000 shades of one single color, depending on what filter you put on top. And then you can combine the image. Otherwise, each pixel will store three points of information, one for red, one for green, one for blue, and that reduces the amount of information that each image will have. So CCDs are 16 bits, so that's very sensitive. Most DSLRs have 8-bit depth, and they take color images. You can also take black and white, but if you take color images, that is divided into 3 parts, so that's less sensitive. So that's still more information than what you would get in like a book, which can only have 50 shades, which is about 5.7 bit depths. Okay, enough bad jokes. All my slides have been in black and white because I wanted to introduce color at this point. So if you're going to take black and white images, the way to add color is to use different filters and then combine them in post-processing. And usually in astronomy, in astrophotography, you can pick red, green, and blue filters. You can also use, if you're trying to image nebulae, which have like emission nebulae, which give out signals in these narrow wavelengths of hydrogen alpha or oxygen and sulfur, you can use narrowband filters that pick out that light. Um, a pop question, you see these dips in the green and the blue spectra where it says HG. Can anyone guess what it is? You can unmute yourself and shout out. And by the way, you can unmute yourself at any point and ask me questions. So HG here is Mercury, and the reason why most astronomical filters, I just took this image from a Nikon website, have this dip is that most street lighting is done using mercury vapor lamps, and to avoid the background light coming from those street lighting, you just cancel it out, and that goes a little way in making your photograph better. These days, if anyone wants to say something.
Yeah, what is this graph about again?
Sorry, yeah, I should have mentioned. So this is the spectrums. On the x-axis, you have the wavelengths from blue to red, and on the y-axis, it tells you like how much of each wavelength is let in by a particular filter. So the blue one is the blue filter. The blue filter is sensitive to all of these wavelengths, the shorter wavelengths, except for this dip, which is where the emission from streetlights is strong. Same for the green filter. It allows green light, and for the red filter, it allows red light. The idea is to use 3 different filters to image your target with, and then combine all the 3 signals together to form the final image.
For sodium also, like they have removed like the whole thing because of sodium lamps. Is that
yeah, right? That is very true. Yeah, sodium and mercury lamps are the most popular. Sodium, I think they just say let's reject all of it because it's, I think, the strongest. But yeah, these days, these lights, as you all know, they are not environment friendly. They've been replaced by fluorescent lighting. That hopefully doesn't cause too much problems in these wavelengths anyway.
These filters would work only with DSLRs, right? Not with CCDs.
This particular filter graph is for DSLRs, but we have similar filters for CCDs too, like broadband filters of red, green, and blue is what we use. There's like a filter wheel that goes over a CCD. And we also have narrowband filters for that. So I'm going to briefly talk about how we do imaging. So we have a 17-inch reflector telescope. By the way, if you can see behind me, this is a 15-inch refractor. It's like a 100-year-old telescope that we use, but only for observations. We do imaging with the 17-inch one. For those who want to have the specs, it's got an f-stop of 6.8. I know I haven't talked about these numbers, and I will do it when I talk about DSLRs, but it's and a focal length of about 3000 millimeters. And we use a CCD camera, which is manufactured by SBIG, called ST10. So this is housed in the, we have an observatory with 2 domes. I'm sitting in the big dome right now, but this one that we use for imaging is housed in the little dome. And it's mounted on this equatorial mount. So equatorial mounts are designed in such a way that the axis of the mount has an angle that points towards Polaris. And once you mount your telescope in this way, it turns around the right ascension axis. So it turns around, it follows the celestial equator. And that helps us to only move it around that axis to track the motion of the stars as they pass the night sky. So this angle of the telescope, wherever you install it, has to be equal to the latitude of the place you are in. So Mississippi, where I'm at, is about 34. In Pune, it will be a bit, the angle will be a bit smaller. And that's the first step. If you want to take astrophotos with anything that gives you a big magnification, you have to track the stars, because the Earth is moving pretty fast, and if you don't track, you start getting star trails. So with this system, let's see how I use the basic elements. So to be hungry for photons, as I said, the aperture or the size of the telescope is fixed. So to take more light in, I have to expose my images for a longer time, and that requires tracking, which I just talked about. You have to track the telescope along with the motion of the sky. But that is still not enough if you want to expose for like more than 5 minutes, or if you want to take like a 20-minute picture, because even if the mount is precise, it's not as precise as to avoid any kind of jittering of the telescope that will make the stars move in the image. So, and this is true for most deep sky objects. If you're imaging galaxies and so on, that you need to guide the telescope. And guiding is the process where sometimes there's another telescope piggybacked on your telescope, like this image, or in our system, there is a little CCD attached that takes an independent picture. And you want to get a bright star in that CCD that you can track, that you can use for guiding. So what the system does is that it looks at how that star is moving, and it gives the telescope a feedback about, the adjustments that it needs to do to bring it back in its original place. So this is like a dual picture while I was taking an image of a galaxy. It's only a 2-second exposure, so what you can see is just the central blob of the galaxy. But if it's a sufficiently bright star, you can take pictures that are as long as 30 minutes and with a stable thing. So that's important for deep sky photography. So to limit noise, I'll talk about like what kind of noise comes up in images. This is also true for DSLRs. So if you take long exposures, so the CCD basically builds up charge, and the electrons that that are responsible for the readout, they have thermal noise, and because of that thermal noise, they are going to appear in each pixel as they're going to show up depending on what the temperature the CCD is at. So we actually cool our CCD down to very low temperatures, like minus 20 degrees Celsius, to basically limit their thermal motion. And even then, we do see them because their electrons are pesky. So what we do is we take dark frames. This is where we keep the shutter closed and take an image of the same time. If it's a 20 image light image, we take a 20-minute exposure with the shutter closed. And the idea is to have the same amount of thermal noise show up, and then we can subtract that from our original image with the object. So this process is called dark subtraction. You can also do it with a CCD. If you're going to take images, what you do is you keep the shutter on. It has to be done at the same temperature that you take the images in. The other thing is seeing. So atmospheric seeing is caused due to like the turbulence, the motion of like what people call, I forgot what the term is. It's called cells of water vapor or something. And so that basically, it's detrimental to the image quality because it kind of shakes the images. It can also happen locally, where if your telescope is in a dome and the dome is warm inside and the outside is cold, then you're going to get currents. Same for the tube of the telescope itself. So for the dome and the tube, you can control the airflow by putting in fans that direct air in one direction. So that limits the seeing due to dome currents. But for the atmosphere, there is little you can do other than pray or try again another night if it's really bad. The third kind of noise is more direct, so you can have some dirt or dust on the camera filter or on the mirror itself, and for that you need to stay clean, but also you can remove that in post processing as well by taking flat frames. So a flat frame is when you look at something that's uniformly bright. We practically do this in sunlight. So while the sun is setting and the sky is clear and uniform, we take pictures of the daylight sky, and that just shows what I'll show you an example frame. So here's like an original of the Bubble Nebula that was a part of my title slide, and it's got these streaks, it's got dark noise, and it's got these big black donut-like things, and that's because of dust. You subtract the dark noise, and then you take a flat frame which only shows these features taken in daylight, and then you subtract this, you do flat fielding, which actually involves not subtracting but dividing the image. And then you get the final image. This has been over brightened to let you see that we have lost these features and so on. So you do this with one filter, you do it with blue in this example, you repeat it with the red and the green filters. Again, for increasing the amount of light, you can work with multiple images. Like this is one blue image, 20 minutes. I can do it multiple times. I can do 5 of these. That increases my time to 100 minutes. Yeah, go ahead.
What does that dividing thing means?
So a dividing will be every pixel has a count. So when you subtract it, you subtract what the count of this pixel is with the corresponding pixel from this original image. Dividing is when you divide the pixel count. And the reason for that is like for darks, a simple subtraction takes out the localized noise that you have. But for flat fielding, you want to think of it as a normalization. So you want to bring uniformity across the image rather than, if you just subtract, you will still get the donuts. You'll still get these features, but with different contrast levels, if that makes sense. But yeah, that's the process. You can do it multiple times to increase your total exposure and then combine. And at the end, you get something that's nice and pretty that you see at the end. So the Bubble Nebula is a beautiful target. You should look at images from the Hubble Space Telescope because they are even crazier. This one, it's not the best image. It's one of the first images I took with the big telescope, but you see these emission features in hydrogen alpha and all these clouds, and it's pretty amazing. So at this point, I'm going to pause the screen share and then show you what I started with. So let me just, am I doing this right? Stop presenting. Yeah. So there should really be a button for that. Sometimes when you're giving a talk, you want to make your audience look at you and not at the screen. So anyway, so about a year ago, I started out with this camera. I hope you all can see it. And this is a Canon M50. It's a mirrorless camera, which is just like a DSLR camera, but it's more compact, it's lighter, but it's pretty much has the same functionality. And you can change the lenses of this camera and operate it well in manual mode, right? So there is nothing special about this camera. I love it because it's given me so many good images. It's done a great job, but this is not in any way specialized for astrophotography. I bought this because it had this flip screen, and there was a phase where I wanted to make vlogs. But as of now, my YouTube channel has 2 videos and 2 subscribers, so obviously that never took off. But anyway, it was about a year back in April when lockdown had started already, and I wanted every reason to get out of my house. There was the Lyrid meteor shower happening at 4 a.m. in the morning, and I said, like, let's just go for it. So I took my camera along. I knew that taking long exposures shows you pictures of the sky. That's basically all I knew. Um, and then I exposed it for, I think, about 15 seconds, and I'll show you the first image that I got. But yeah, this camera I got it. So it's a beginner level. It's equivalent to a beginner level DSLR. So it's kind of it's budget friendly for a grad student. If you've worked with DSLRs, you know that there's much more sophisticated options available in the market. But that's what I just started with. Also, to take long exposures, you need a tripod. You can't hold the camera in your hand, and for any photo that's longer than a second or something. So I'm gonna go back to sharing my screen. So I went there at 4 a.m. in the morning and then pointed up in the sky. I'm missing some meteors because of that, but that's kind of what my first image was. So I knew one rule: you have to expose your image for a long time, but I did not know anything about focusing. Look how crappy that is. But I was really excited. Like, I was jumping when I opened this photo because you can see hints of the Milky Way, something I had never captured before. So that got me excited. Then I learned how to focus my camera in manual mode. I went back there a week later and look at the difference. This just comes from focusing. This is a single image, about 15 or 20 seconds in terms of duration of the exposure. I've used a 15 millimeter. I used the kit lens for that. I hadn't even bought any lenses at that point. It's a cool image. You can see Mars on the left, Saturn and Jupiter pointing in a straight line towards the Milky Way.
I want to clarify one thing.
Mm-hmm.
Are all these images 15-second exposure shots?
Can you repeat the question? Sorry.
Are all these images 15-second exposure shots?
By all, so only these two that I've shown you, they are 15 seconds. The one I showed you before, they had different exposures.
Like, I've tried with the 15-second shots, but they don't get a good quality image so as to focus the Milky Way. Like, I just get to see a few dots with the 15-second thing. I thought these images would have been taken with 32-second exposures.
So I think it makes a difference in this case. These were really dark skies. Okay. So these were taken from a remote location. That might make a big difference. But in my experience, 15 seconds has been enough to capture an image like this. You can also use something like Lightroom that helps you, or some image processing software that helps you adjust the contrast levels. Like, this image does not look like this out of a camera. And I'll tell you about that also. So for using DSLRs, here's a few to-dos. So you have to use manual mode, be able to focus. As I said, find a bright star or a planet, get the focus right. Try to get that as sharp as possible. It helps if you use the live view magnification feature. So shutter speed, try to go as long as you can. So with DSLRs, if you don't, I don't have a tracking mount for a DSLR. Those things don't come cheap. So you need to be careful about avoiding star trails. So if you take too long of a picture, the stars have moved and they cause trails on the image. So there's a rule which is called the 500 rule or 300 rule. So 500 if you have a full frame, one of the more expensive cameras. Otherwise, if you have a crop sensor camera like mine, it's a 300 rule. So what it basically says is that the longest possible picture in terms of time that you can take can be calculated by 500 or 300 divided by the focal length of your lens. So, like for those not familiar with uh, DSLR like photography, the focal length is what gives you the magnification of your image. So wide angle lenses have shorter focal lengths, like this one has starts from 15 millimeters. So if the focal length is going to be short, the longest possible exposure, this number is going to be bigger. So for wide angle lenses, you can imagine you're looking at a bigger chunk of the sky. So that's not going to move a whole lot in a given amount of time, as opposed to if you're looking at a really, really magnified thing, those things will move out of your frame a lot faster. So that limits how long you can expose. So this is quite a nice rule of thumb to calculate like how long an image you can take. When it comes to aperture, again, use the widest possible. This is sometimes quoted as an F number. So this is the ratio of the focal length of the lens to the diameter of the opening of the lens. So again, this number has to be low to make sure that the aperture is widest. For astrophotography, what's desired for, say, Milky Way shots or something like that is f-stops. I would say less than around 2 are optimal, less than 3 work well. So that's one thing. And then the third thing is ISO, which is a number that determines how sensitive your sensor is. So you can crank up the ISO and make your sensor more sensitive. So even if you take the same exposure in terms of time, you have the ability to display more signal. But again, this is something, if you get too greedy, then if the sensor is too sensitive, it's also sensitive to noise. So you don't want to keep your ISO too high. I usually keep it around less than 1600. This changes with what the target is, of course, but if you're starting out, you can just keep the ISO on its auto setting and it will make sure that it's not exceeding too much. And another thing that's important is to be able to stack multiple pictures for the simple reason that noise being not correlated. If you stack several pictures, the noise will cancel itself out, whereas the signal, you can start seeing dimmer and dimmer things in the same field. So here is an example of what a single raw image looks like out of a camera, as opposed to what a processed stacked image would look like. And so this was taken in super dark skies in Utah. So getting something like this amazed me also. I did this with a wide angle lens that I had bought at that time. It's a 12 millimeter, so that's 12 millimeter, and I think it goes down to f2. So you can get really wide shots, collect a lot of light. And this being wide also allows me to take exposures that are closer to half a minute. So that was the settings. That's a single image, but I took 30 of them, stacked them all together. This is a composite, by the way. So the ground that you're seeing was taken just after sunset, where it was brighter. And then the sky part is something I had stacked, and this pulls out so much more detail. The focus was good. Obviously, there was Jupiter and Saturn, but you can see these the dark nebulae in the Milky Way, the dark clouds, and yeah, it's really amazing what stacking can do. Um, and the great thing is there's free software available for you to stack your own images. All you have to do is make sure there's a bunch of stars visible in the frame. And then there's one called Sequator. I hope I've put it in the slide, but if not, I can post it in the chat later. So Sequator is a free software that's really easy to use that you can use to stack your images. And then once you get to do these kind of things, you enter into the realm of art. So you try to frame your shots in creative ways and then play around with color. I'm not a big fan of adding like I like keeping things in natural color. You can only play with the white balance, but sometimes it's fun to experiment with, in post processing, adding color to bring out some other details. Like in this one, you can see more clearly the dark clouds and the dark lanes in the Milky Way. And of course, you can make pretty pictures, and you can have it's really fun processing images later. A few examples, Equator shots. The one on the left, there's the Pleiades and the Hyades star clusters. This one on the left, you can see it's got more noise, so I haven't stacked it a lot, a whole bunch. Again, another shot of the Milky Way. This time the white balance is too off what's natural, but I was having fun with composing it on a grassy field.
Yeah.
Yes.
What is white balance?
Oh yeah, so white balance is you can artificially define what white is on a spectrum. So I'll give you an example with the human eye. Human eyes are also like cameras, right? And we are wired to see white in terms of daylight. So for us, daylight, like the level of whiteness we have in daylight is what our minds are set towards. But that is something you can shift in the spectrum corresponding to temperature. So you can make images appear overall. If you increase the white balance, you will feel like the images have been taken on Mars or something, where you have more of a sepia kind of look to it. Or otherwise, in this middle image, everything looks like shifted towards the blue. So that's a change you can make in the camera setting as well as post-processing. Another thing you can do is artificially remove stars from your image if you just want to show like the milky part of the Milky Way. That's also something you can play with. I mentioned human eyes also being camera, so the exposure that the amount of time the human eye is exposed for each image is about 0.1 seconds, like a tenth of a second. And I don't know if there's any like neuroscientists or someone in the audience, you may talk about why we are wired in this way. Like the refresh rate of our images as we are seeing the world around is a tenth of a second. And that's why when you look at the full moon, sometimes even the full moon is too bright for a tenth of a second. If that refresh rate had been faster, you could have seen more details of the full moon. But sometimes the full moon, you look at it and it's too bright. You can't see any of the mares and so on. So with star trails and wide angle lenses, you can have a lot of fun composing it against different backgrounds. Like this image was taken with the moon rising behind these set of trees so that you can get their silhouettes. In the middle, you can see hints of the Andromeda Galaxy. So that's a target which I haven't done using high magnification lenses, but it's in long exposures. Again, it's something it stands out and it looks quite good. You don't need to have the 500 rule or tracking if you want star trails. You just keep the shutter of the camera open and let the trails form. And that's also fun to do. You can look at the North Pole, expose the camera, and get the motion of the stars going around the pole star. Here I've done it close to the equator, so you can see stars along the north have a little curvature, the stars going to the south, curving in the opposite direction. Then about when I started, like a month after I started clicking photos, we were all lucky, I think, to have this beautiful comet. And I spent a lot of time chasing it, and I've written a blog about it. I've also been intending to write blogs about my photos. Haven't got around to that, but I'm happy that I'm giving this talk. I hope that'll get me started on writing about that too. But neo-wise, in terms of photographing comets, you treat it kind of like the Milky Way, but you actually treat it as something like the Pleiades. If you want to image the Pleiades with a wide-angle lens, you need exposures about 10 seconds in length, and that brings out the tail of the comet and everything. So here's the Pleiades. It's in the same exposure. You can see the Pleiades quite clearly. Venus was in the Taurus cluster at that point, so this was again a very nice image where a lot of things could be captured in one go. But I did not have a lens that magnified things better than that, so you must have seen like crazy images of the comet with details of the tail. That's something I couldn't capture with a wide-angle lens, but I had fun like waking up at 4 a.m. and clicking these shots where I could get the comet in front of different landscapes in my town. This is when I tried to capture it through a telescope. So by that time I had bought for about $30 this thing called a T-ring. So this basically lets you attach your DSLR to any telescope by taking out the eyepiece, and you can just plug in your telescope there. And this has been my best investment ever, because not only has it let me capture shots of the moon and the planets, but also like looking at the comet was cool. You can't quite see the tail because it's too high a magnification, but you can see the coma really well. And it also tells you how much it's moved with respect to the stars, because the comet's like close to us, so it's got a bigger proper motion. In terms of bigger magnification, I found this little mirror lens, which looks like a cute tiny telescope. It's got a 500 millimeter focal length. Again, there's free software that let you stack images with deep skies. It's called Deep Sky Stacker, I think. So you can take beautiful images of the Orion Nebula, which is nice and bright, and then they don't have to be super long, like 5 to 10 seconds at a time, and then stack them. When you're doing these kind of images with, say, lenses with longer focal lengths, you can go through the same process, like take frames with the shutter on, so take some dark frames, take multiple of them, stack them together, and that can give you good results. A fun thing, when I took these images, I had forgotten to take any dark frames, but the temperature outside there then was about 4 degrees, and I just figured, okay, I couldn't do it while I was outside, but our refrigerators have a temperature of about the same. It's about 4 degrees inside, so I just kept my camera and the lens inside my fridge and took a bunch of dark frames just with the shutter on. So be creative. It works. A few shots through a telescope that I was able to take. There's one with the Pleiades. There's Albireo, a double star. Imaging planets is a little bit different. You have to, of course, have a telescope. Just taking a look at the time. I've got about 5 minutes, so I'll cycle through the images that I have relatively quickly. With planets, the technique that we use is called lucky imaging. So for planets, the atmospheric seeing and the scintillation I talk about it matters way more because if you observe planets through the viewfinder of a camera, if you have set it up, they appear to move like jelly. And that it's they're super sensitive to seeing. So what we actually do in practice is we shoot a video. Um, what I've called a 1:1 video is that sometimes cameras they downsample the actual frame to create the video into the resolution that you want, like 1080p or whatever. My camera has an undesirable trait for videographers in that its 4K mode has a massive crop. So anyone who shoots videos hates it, but it has this one-to-one feature where the entire each pixel is counted as one resolution pixel in the final video. So that's something I've been able to use to shoot videos of planets. And once you have a video of a planet, what we do is that in practice, this atmospheric seeing at some particular instances, everything lines up in a way that the image is crisp. So, and that happens very rarely. Like it might happen, I don't know the rate at which it happens, but if you shoot a 1 minute video, which has over a couple of thousand frames, about 10% of those frames, about maybe less than 100 frames, will have this lucky capture. That's why we call it lucky imaging, where everything lines up and the frame itself is sharp. So the idea is to pick these sharp frames and then stack them up together to get the final image. And again, there's free software like AutoStacker and Registax that can let you, if you have a video that you can use to do it. And these are the images of planets that I've been able to capture through a 12-inch telescope. And here's where I wanted to pitch, like a telescope like this would be great on the rooftop of the academic block. Because you don't need dark skies. Well, deep sky photography is sort of hopeless in a big city like Pune. But if you want to image the moon and the planets, it's super doable. And I think you all should pitch for getting a telescope like this. A 12-inch or even an 8-inch telescope is really good. And play around with taking cool images like this. And the difference that, stacking these free software like AutoStacker, they make in getting things like the division between Saturn's rings, or the you can, in the Jupiter's image, you can see the big red spot. You can see a couple of moons. I think that's Europa that was about to not transit. I think it was about to go behind the planet. And it's amazing. Another thing I should mention is all these pictures. Well, that's Uranus, by the way. This is kind of fake. It's really hard to get the disk of your Uranus resolved because it's so far away. But I was happy to get the color out of the image. So all these planets were taken when they were in opposition. So that's the best time to click pictures of planets, because they are exactly opposite to the Earth with respect to the sun. And that means all of sunlight is illuminating them. And that's the point in their orbit where they look the brightest. So last year we had oppositions of Saturn, Jupiter, and also of Mars. So Mars looked as big as it would for about 20 more years. The moon is an easier target definitely with a telescope. It's horrible with a smartphone. I have countless images like this in my phone where the moon is looking really good. I pull out my phone and it gives off something like that. But with a DSLR attached to a telescope, you can easily pick out the craters. The moon is super bright, so the exposures that you need to take don't have to be long. They have to be like maybe 1/100th of a second, as short as that. So you don't need to worry about tracking or anything. All the other elements still do apply. It's helpful if you take a bunch of shots and stack them together, and then use some sharpening tools to get like some detailed features. These have been taken with the same kind of process that I described for the planets. I shoot a video first, and then I use the processing software to try to get the surface details out. You can do the same for the sun. We have a few sun filters that can enable us to safely point the telescope at the sun without burning the camera. And if there's things like sunspots, we can try to get those. These are shots that I'm really happy about because this takes a lot of luck. So sometimes the International Space Station, depending on where you are, it transits the sun or the moon. It was going to happen on Friday, but well, Friday was full of bad luck. But I've captured this transiting the sun again through a video. So the ISS, if you want to get the details, I kept the exposure at the shortest possible, which is like 1/4000th of a second, because the ISS is moving so fast. In an individual frame, if you want to get details like the solar panels, you have to be really quick at taking those pictures. So this is also something worth experimenting with. Again, you can do this with a telescope on campus. How cool is that? Sometimes you have things like your camera falls down and you're holding a red flashlight and it just makes art. I have nothing else to say about this. You can, I'm usually really annoyed with clouds all the time, but sometimes you can use them also in long exposures. They can have this nice fuzzy motion if they are moving, and you can try to get the stars in the background. That's the Big Dipper. That's the ISS flying by. You can have fun with lasers in long exposures. Again, this is an image with a white balance that's saturated towards the red. And then you can try to shoot lasers at the center of the Milky Way and see what happens. You can take composite images. This is where you want to image a target that's close to you and a target that's away from you, and that requires either two different focal lengths or exposure times. So this was when we had in December the Jupiter Saturn coming close together. This is through a small telescope where I wanted to get it at the background of this little tree. So in a composite, this you can do in Photoshop. Photoshop's your friend. You can combine multiple exposures and then get the detail out of it. Composites are fun. So the Jupiter-Saturn conjunction, by the way, was very low on the horizon, so it was something to see with the eye. I tried capturing pictures, but when something's on the horizon, there's just too much seeing there to get anything out of it. Composites are fun with the moon, with a high magnification lens. If you want to get buildings, you need an exposure that's longer, but if you want to get details on the moon, you need a short exposure. But then you can put them both into Photoshop and then combine them to get a composite. And I think a lot of things look better in black and white. You can try to get earth shine. That's when the moon is in a crescent phase, but the unilluminated part of the moon shines because of light reflected from the earth and coming back at us. If you overexpose the moon, well, the phase of the moon is gone, it's overexposed, but then you can get detail out of the dark side of the moon. And then you can combine the two. This isn't a great effort, but you can Google images which have these composites that look really good. And to end with, I'll just show you the thing that I had the most fun with last year. It was a summer night, and I decided to spend two hours at the dark site that we have close to the town here. And again, I was bored, had nothing to do. And in spite of all the mosquitoes in Mississippi, I just took a shower and bug spray and then went there and took a series of 30-second exposures, phased a minute out. took a bunch of them and just got this beautiful time lapse of the Milky Way rising. And you can see intermittently some satellites flying in the image. I don't think I got any meteors. Um, Close to the trees, you can see some spots moving. That's fireflies, and they were also a lot of fun to capture and play with. You can also see Jupiter and Saturn rising towards the end of the photo, and it's just like so much fun. Like I never imagined I would be capturing things like that, and that's kind of the thing that keeps me going. So that's kind of the end of it. Like I tried to show you most of the nice pictures I have at the end, but thanks for listening. And I'm happy to have done this talk today since we couldn't do it on Friday, and you've been very patient. And now it's your turn. Like I'll be happy to answer any questions and talk more about this. Thanks again, Aakashganga, for having me.
Yeah, thank you for that great talk. The pictures are really nice.
Thank you.
So the telescope you were talking about in the slide about lucky imaging, it is 8 inch, right? Did you say 8 inch?
So this one's a 12-inch that's mounted on our
Okay.
rooftop. But 8-inch is also really good for planets as well as the moon. This is actually too big for the moon. With an 8-inch, you can get like the whole half moon in one frame.
Right. So we do have one 8 inch, like
On campus?
yeah, like a senior made it for a Ayuka workshop, if I'm not wrong, and he left it there.
Oh, so is it like a Dobsonian kind? Or is it mounted in this way?
It has a like tripod, not tripod. It is. I can't
It might
describe
have
it.
one of those that moves like this way and then up and down, like altitude and azimuth kind of thing. So I mean, even if you can't mount
Yeah,
it,
it's like that only. Altitude and azimuth. That.
right? Yeah. With those, it's hard to track unless you're able to mount them at an angle pointing towards Polaris. But you'll still be able to get good moon pictures out of it. So the moon doesn't need a lot of tracking.
So were most of your photos taken by your camera that you showed today?
Yes, that's right, and that's the thing that surprised me also. In this photo, you can see it's the same camera that's attached to the 12-inch. All these star fields and Milky Way and the moon shots have also been taken by that. So, yeah, these days the equipment, and I think like the advancements that today's DSLRs have, like no one made these for astrophotography. Like these are still being made for usual photography, but they're really good if you want to capture night shots. And I was talking about smartphones. I've seen the new Google Pixel, the new iPhones. I don't know about the other ones. Can capture. They have the ability to take long exposures, so you can get the Milky Way out of them. You can also get things like Orion Nebula. I mean, the nebula kind of looks like a fuzzball, but it's still it's still crazy that you can get those things out of a phone.
There are some questions in the chat.
Oh, let me hop onto there. So yeah, asking me about Oh, I missed most of the nice comments you've had in the chat. Location really important. You have to get to the darkest skies that you can, like go on treks. I don't know. I've never, like, if you go to Pashan Hill, I don't know how much it's better, but definitely try to get out of the city. Um, how much of an
I was
upgrade
actually
is it?
trying to ask where you shot. When I posted that location thing, I was trying to ask where you took your first picture from, the one of the Milky Way.
Oh, I see. So that was taken, like I live in a small town, Oxford, so it doesn't have a bunch of light pollution, but it's still a town. So it's like a place, 15, 20 minutes of a drive outside. So it's a really rural part. And it's got good dark skies. So that's what we actually use for teaching, having sky gazing sessions for our astronomy labs. So it was taken through a dark location. Thoughts on Starlink? Annoying. I haven't have had them come up in my images yet, but you see on Twitter, you see like mm, it's one thing that it just shows up, but when it starts happening in the big sky surveys for the science images that are really important, and you get those streaks of light passing through, I think um, more thought had to be gone into that before sending them out. And now they are saying that they will try to align the solar panels and use different materials which have lesser reflectivity, which I think they have to do. But why didn't you think of this before?
Aren't they like liable or anything? Like, well, can't the astronomers do anything to stop them if they actually don't care?
There has to be
Yeah, I
regulation.
wouldn't say. Yeah, this the astronomy lobby, if it exists, it's not very strong, right? So we are always, unless we are loud about it and vocal about it, no one's going to think of this as an issue. So that's one thing we need to do, is bring this to people's attention and really make them understand why they're important. Because I mean, Starlink it really does have a good purpose.
Yeah.
Um, right? I'm not saying don't send Starlink, but again, this has to be well thought out. So we need more communication between scientists and policymakers that have an actual say in these kind of things. Trying to find other pictures. Yeah, CCDs are also used in DSLRs. That is correct. I don't know a great deal about that. Like, I think CMOS sensors are commonly used, but you have for sure DSLRs have CCDs too. But again, the astrophotography ones are um, they might be different in having the 16-bit depth. But again, cameras are improving every day, so there's some nice astrophotography specific cameras also, like Canon EOS RA, which is more sensitive to hydrogen alpha light. I wish I can afford that someday. Any other questions? Yes. Can I superimpose multiple 15 seconds to get quality like 32 seconds? Yes. It's not additive in a simple way like that. So two 15-second images don't make a 30-second image. If you want to stack them in a way to reduce noise, like if you can just add them together, but that will also add the noise. But what in practice, if I have 5 pictures of the same scene, and if I want to stack them, I'll take the first picture, I'll add a layer on top of it with the second picture, but then reduce the opacity or increase the transparency of the second picture to like 70%. And then the third picture is about 50% of its original opacity. And that's the way stacking is done. The software also does it. So you can do it manually in Photoshop, or you can use something like Sequator to do that. So the exposure, the effective exposure adds up, but not linearly. But the more pictures you can take, the better. For somebody living in a heavy light polluted city, is it worth buying anything even to look? That's, let's see, for a heavily light polluted city, you can still chase the moon and you can still chase planets. And for something like that, if you get like a 6-inch or an 8-inch reflector, I think it's still worth it. You can also like actually, even if you have light pollution, you can try to image things like Andromeda or the Orion Nebula. I know there's a really funny YouTube astrophotographer, I'm going to type his name, called Astro Biscuit, who does some imaging from London. Like not central London, but definitely he's London based, and his YouTube channel, I would recommend you checking it out. He talks about how you can use basic equipment or modify equipment in a really cost-effective way to be able to click pictures regardless of the conditions. You can definitely, if you don't want to buy a telescope, if you have a DSLR or you can borrow one, you can definitely try to get a few lenses. Like for the moon, you can get something that's high magnification like this one. Or a wide angle lens, you can experiment with getting constellations and stuff like that, even from a city.
The logo for this Astro biscuit is so similar to Astro White.
Yeah, that's by taking
the
out
biscuit.
of cookie. Yeah, that's very similar. There's also Astro Backyard. There's quite a bunch of YouTubers popping up that will walk you through the process of like Astro Backyard. He has proper expensive gear, but then he makes really good videos on how to do the processing. He walks you through the process from start to end. He's got some nice tutorials.
Did you miss this question by Tushar Oja? How much of an upgrade is a DSLR or a good large sensor?
Yeah, I did miss that. Thanks for pointing it out. As I said, I don't really know much about the smartphones and like never worked with one. I have a cheap ass little phone which is good for nothing. So for now, I would still say a DSLR is a really good upgrade. But who knows, like in a couple of years, all the work I've spent trying to get the good Milky Way shots, someone will just pull up a smartphone and do the same thing, and that'll be hard to take. But I think it's really cool if they have the ability to do that. So, like, I'm sorry, I don't have an answer for you, but one thing for sure is that DSLR is so much more fun. Like, you get the sense that you are doing it, you're creating those images, whereas anything automatic, you get a good output, but the fun in the process is gone.